14 UT sharp. So today we have presentation by Olga Khabarova. Dr. Olga Khabarova received her bachelor's degree in geophysics in 1994 and then master's degree in solar terrestrial physics in 1997, both from St. Petersburg State University, Russia. Then he moved to Moscow region and got her PhD in 2004 from Izmiran, Moscow. And in particular in Izmiran, she has developed her own midterm prognosis of geomagnetic storms using data of both near-Earth missions and geomagnetic field data from ground observations. So now she is senior researcher in the Heliophysics laboratory in the Pushkov Institute of Terrestrial Magnetism. Her areas of expertise are observational studies of solar wind, large-scale structures, current sheets, turbulence, and particle acceleration. She has impressive list of services in national and international committees. She is frequent referee for all main journals and many funding agencies. And today, Olga will talk about solar and local sources of solar energetic particles in wide energy range. Please go ahead.
Thank you very much. Thank you for inviting me. It's a great pleasure to be with all of you here, virtually at least. And today I would like to talk about energetic particles as we observe them at 1AU in the heliosphere, how they propagate, where they originate, and so on. During previous talks given at this seminar, you learned from specialists in solar physics how particles can be accelerated at the sun. And my role here is to show how we observe them and how they propagate as well. So, okay, I'm trying to run my presentation. This is a typical example of observations of particles of these energies, KeV and EV energies at 1AU. Now I'm talking about observations by three spacecraft, Stereo B, ACE, and Stereo A. ACE is located in the Lagrangian point, the first Lagrangian point between the Earth and the Sun, and two these guys were located nearby the Earth, not very far from it, but a little bit. Stereo ahead was located a little bit ahead of the Earth, and Stereo B was located a little bit behind the Earth. So they are called Stereo A and Stereo B. And this mission, Stereo mission, actually allowed us to investigate propagation of energetic particles in every detail, in more detail than before. Because if you just measure something in one point here next to the Earth, then you have just some small piece of information from the whole picture. Of course, if we have 3 points of view, then we can trace structures and understand properties of energetic particles. So it was clear that if the sources of energetic particles are somewhere far, for example, at the sun or near the sun, accelerated by IC-driven shock near the sun in the corona, then we will observe the energetic particle flux enhancements practically simultaneously in this configuration. But if the source of energetic particle is local, then the observer will see first observations of this enhancement with Stereo B, then with ACE, and then with Stereo A, because the solar wind will rotate a little bit, structures will rotate from here to here. And the prior talks as I told, gave us examples of particle accelerations and very serious studies of processes occurring at the sun and in the corona. So I will not repeat this. I just refer to previous talks. And now, if you look at what happened in the solar wind, you will see that major sources of energetic particles that can accelerate particles are, of course, ICNEs. ICNEs are interplanetary coronal mass ejection, and CIRs, characteristic interaction regions. Characteristic interaction regions are shown here in this modeling as rotating swirls, these leaves, and ICNEs propagate practically radially like big bubbles. So ICNEs push shocks in front of them. It's shocks, ICNE-driven shocks are formed in front of them, and as well, interplanetary shocks are formed at edges of CIRs. So for a long time, it was thought that the main sources of energetic particles of keV-MeV range are shocks of different kind, both ICNE and CIR associated shocks, and of course flares, some active processes at the sun, and of course the quiet time, the ground profile of ion differential energy spectra is quite smooth, but depending on the situation, you can see increases of energetic particle flux due to some processes that actually occur both in the solar wind and at the sun. So this is the dominant paradigm that we can have energetic particles of keV-MeV energies, mainly from distant sources, from shocks formed at 2,3 AU by CIRs and shocks preceded ICNEs, as well as due to flares. This is just a kind of sketch about this. You can see main sources as people thought that they exist. So this is ICNE, and particles can be accelerated both during flares and due to diffusive shock acceleration. And the same mechanism is thought to be responsible for particle acceleration at 2,3 AU, and then particles come back to the Earth, and nothing happens directly in the solar wind besides some DSA, still diffuse shock acceleration at shocks which come to, for example, 1 AU or 5 AU, whatever. And there are, of course, a lot of publications about particle origination and propagation in the solar wind, and I just list some of them. This is a short list, but it's my preferences, and I especially recommend the last very recent book edited by Olga Melandrake and Norma Crosby. And if you want to know how these ideas about particle acceleration of the sun and the shocks are developed, please read this book. I highly recommend this. But during the last several years, it became obvious that there is something beyond classical mechanism like DSA and flare acceleration, because sometimes we observe some energetic particle enhancements which are obviously local because they are observed by different spacecraft with time delay corresponding to the propagation of non-energetic solar wind. So it was found out that actually we have all these mechanisms, classical mechanisms, and as well particles can be additionally accelerated, reaccelerated in magnetic cavities, so-called magnetic cavities formed by strong current sheets. And what is important, inside those cavities, there are dynamical, small-scale magnetic islands born by turbulence, due to turbulence and as a result of magnetic reconnection at strong current sheets. So typically, if we just consider the particle acceleration at current sheets and in small-scale magnetic ions, the energies will be not very large, about keVs. But because of the ability of magnetic islands to trap energetic particles, and because of the ability of magnetic cavities confine energetic particles and the structures like small-scale magnetic islands, we have very strong reacceleration of energetic particles. So these are local sources of energetic particles in the solar wind. Some examples. Typically, not typically, usually, so-called atypical energetic particle flux enhancements of events are observed, as I told, in plasmas associated with magnetic islands and current sheets. Here you can see quite typical SAP event, and before the arrival of these energetic particles, you see these jumps in energetic particle flux observed up to 2 MeV, 1 MeV for sure. And I say jump, but it's not actually jump. If you look at high resolution data, you see that it lasts for hours. And behind the ACME, the trailing edge of ACME, again, we can see the same. What is important, as I told, these are typical energetic particle events are observed with time delay by two spacecrafts, Stereo B and Stereo A, as shown here. As you understand, for energetic particles of these energies, this distance is nothing. So if these stars would be somewhere far, we would see this quite simultaneous increase in energetic particle flux. And this is the example of a typical energetic particle event associated with CIR, near the CIR. This is a classic increase of energetic particle flux up to several
Olga,
energies.
could you repeat just what CIR stands for?
Co-rotating interaction region. You remember those sleeves rotating in the direction of the rotation of the sun? They come from coronal hole flows. They are formed by coronal hole flows. If the coronal hole exists for a long time, long-lived coronal hole produces so-called co-rotating interaction region. And these regions, they interact with the slower solar wind and form wave on density on its front. So people see them, observers see them, a different spacecraft like Stereo A, Stereo B, well separated, with time delay. It's a quite well-known phenomenon, but what I'm talking about, not typical energetic particle flux enhancement associated with CIRs, but these enhancements, which can be as strong as typical CIR enhancements, which are related to crossing of the heliospheric current sheet here and here, and as well as it was shown, it was related to the occurrence of small-scale magnetic islands near the heliospheric current sheet in the cavity between the heliospheric current sheet and CIR. And of course, the most classical events when we have no high-speed streams, nothing which can be blamed for sources, to be source, external source of the energetic particle flux enhancements. And of course, this is the crossing of the heliospheric current sheet or heliospheric plasma sheet, which surround the heliospheric current sheet. And you see this ion flux, energetic ion flux enhancements seen right when we cross the heliospheric current sheet in some vicinity, and these are hours, practically one day. And this is not very unusual situation. Sometimes we observe this with some regularity, and when we started to work on this in 2012, I was puzzled actually, because it was not clear for me why sometimes I see this clear energetic particle flux enhancement associated with the crossing of the heliospheric current sheet, and why sometimes I see nothing at all. I tried to calculate typical characteristics of this heliospheric current sheet, like strength and etc., and I could not find anything. And finally, when we start working with Gary Zhang's group on particle acceleration associated with small-scale magnetic islands in the solar wind, I realized that that's it. When they have a lot of magnetic islands around the heliospheric current sheet, we see every time strong, relatively strong enhancements in energetic particle flux. If the heliospheric current sheet forms kind of a ripple, it's very easy for these ions to be trapped inside this ripple, and this system actually works simply as a natural tokamak. And let me formulate what are atypical energetic particles events. Typical energetic particle events, you know a lot of literature about SAP events, solar energetic particle events, both impulsive and gradual, and Sierra associated energetic particle flux enhancements. These categories show very similar profiles of energetic particle flux and are typical energetic particle flux enhancements. They every time observed with a time shift typical for the propagation of a certain structure and the solar wind. And we actually checked for every signature of local processes, and it was confirmed that every time when we see these and atypical energetic particle events, actually they are related to crossings of current sheets or magnetic islands. So if we are talking about the current sheets, the first, what everyone can imagine, the first mechanism what comes to your mind is, of course, magnetic reconnection. And the ability of magnetic reconnection to accelerate particles to wide series images up to MeVs, keVs at least. It was known for years in the magnetospheric physics. And several years ago, maybe 5 years ago, there was a very strange situation in our science when magnetospheric physicists all knew about particle acceleration by magnetic reconnection, but the observers, especially observers who work with solving data, they were not sure about this because of this paper of Jake Gosling, who the title of the paper was "Absence of Energetic Particle Effects Associated with Magnetic Reconnection Exhausts in the Solar Wind." And every time when nice theorists got results like we see particle acceleration due to magnetic reconnection with parameters typical for the solar wind, everyone got this reply from the referee, but Jack Gosling said that there is no particle acceleration associated with magnetic reconnection. And just several years ago, the situation has changed because the number of evidences for local energetic particle acceleration was too large to ignore it. So what was wrong with the Jake Gosling paper? I must say that Jake was a brilliant scientist and talented, and of course he practically opened eyes of many people for magnetic reconnection in this solar wind. But what about energetic particles? He suggested that Petchik-like magnetic reconnection, he was looking for Petchik-like magnetic reconnection, and suggested that it should produce low energy particles of this range, maybe maximum 50 keV, 50 keV energies. And he tried to find something at near very strong reconnection exhaust, and found practically nothing in this energy range within this time range in minutes. But the problem was that he was suggesting a kind of situation which maybe was not quite correct, because actually there is a strong enhancement around this very point. This is the same reconnection exhaust. If you look at wider time range and at larger energy range, so it became obvious that actually particles are accelerated by current sheets, maybe not only current sheets, because theoretically current sheets can accelerate particles up to maybe 100 keV, but not to any of this. What happens with this particular case? We have shown that it was a case of fragmented ICMEs, and this magnetic reconnection occurred at the edge of twisted magnetic cloud, twisted and fragmented, and some mechanism related to magnetic islands, which were quite rather big here in this particular event, was acting. So if we look at some statistical results concerning reconnection exhausts, and as well simply all kinds of covering structures, including different discontinuities, current sheets, shocks. Every time we see energetic particle flux enhancements somewhere nearby the crossing of these structures. And here we used 126 reconnection exhausts, which were identified by Jack Gosling himself. So it's not that simple and that easy as people thought before, and obviously there are some mechanisms which can accelerate particles locally in the solar wind. And as I told, every time when we observe these strange, atypical energetic particle flux enhancements, they are related to some magnetic islands and current sheets. Actually, it's practically the same in terms of turbulence. Every current sheet, if it's disturbed, it produces secondary structures, produces magnetic islands at different scales, and if a current sheet reconnects, you will see these bubbles, you will see magnetic islands nearby. Hope they are then deflected and from this position, location of the mothering current sheet, and as a result we observe this situation, as I told. This is a scheme of heliospheric current sheet ripples and magnetic islands inside the ripple. By the way, this leads to very interesting effects on observations of crossings of the heliospheric current sheet. I have no time now to discuss this, but for observers it's sometimes very puzzling to see how electrons, suprathermal electrons, behave near the heliospheric current sheet and inside the heliospheric plasma sheet surrounding the heliospheric current sheet. So it's a lot of effects, brings a lot of effects. And the second point, why Jack Gosling found nothing, considering very classical Fetchik-like magnetic reconnection exhaust, because actually magnetic reconnection in the solar wind occurs here and there, here and then stochastically along the entire current sheet. If it is strong, it reconnects stochastically, like in this Lazaran's paper. So the reality is a bit more difficult, complicated than people thought. And regarding concerning the magnetic islands, as I told, we treat them as a consequence of turbulence, well-developed turbulence, and as well as a consequence of magnetic reconnection. And sometimes people ask me what is the difference between magnetic islands and flux tubes, because it's very they have a lot of papers about magnetic flux tubes in the solar wind. And I can say that from the observational point of view, there is no difference, because if a spacecraft crosses magnetic flux tubes, this is experiment in laboratory plasma, and we have two flux tubes with time and distance from the source. Those flux tubes, they twist and merge, and magnetic reconnection occurs, and finally it was shown even in the laboratory plasma, and finally we get a mixture of flux tubes and magnetic islands. So the crossing of the heliospheric current sheet actually looks like something like this. It's current flow in the main current sheet, and the magnetic islands and the waves and the secondary current sheet, and magnetic reconnection occurs here, 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 and there, everywhere around. So if we look at propagation of magnetic islands in the solar wind, and distribution, spatial distribution of magnetic islands in the solar wind, of course we can observe them near the strong current sheet. And there was a very nice paper showing that the number of magnetic islands increases near the heliospheric current sheet. This is a time to sector crossing in days. And actually we even can calculate the size of these magnetic islands, suggesting that there is not only source locally in the solar wind, where we absorb the magnetic islands, but largest magnetic islands can come from the corona, and then they expand on their ways. It's practically not investigated. It's very new, so we are looking forward to getting new results on this. And what is important, you can now, there is an opportunity to work with the database of flux ropes reconstructed with Grad Shafranov technique. Tian Hu with colleagues from University of Alabama in Huntsville, they do this tremendous work, and please look at the recent papers and look at this database. because it's very interesting. If you are interested in this topic, you will find a lot of interesting features like that. Yes, someone wants to ask anything? No. Okay. And this number of these magnetic islands or flux ropes follows this cycle. It's very interesting. It's understandable, but it's very interesting picture actually. And again, coming back to particle acceleration, we see every time when we cross the heliospheric current sheet, which is surrounded with magnetic islands, dynamical magnetic islands, what is important, because if everything is stable, nothing happens. Particles can be accelerated by just stable magnetic islands. And in this particular paper, we showed that we traced the crossing of the heliospheric current sheet and show the merging of magnetic islands and show the elliptic particle flux enhancement associated with this. And as well, we showed this there is nice rotation inside these regions, characterizing the presence of magnetic islands. And once again, this is a heliospheric plasma sheet crossing. Very this is the angle, clock angle of the solar, the interplanetary magnetic field, and you will see these variations characterized in crossing of the borders of magnetic islands. And what is interesting, there was nothing around, no high-speed streams, and we saw these enhancements in energetic particle flux. So sometimes we can get this energetic particle flux enhancements even without crossing the heliospheric current sheet or without crossing any really strong current sheet, because of a very nice situation when interaction of differently streaming with different speeds produces swirls in the corona, and this swirl propagates further in the solar wind, and then because it becomes fragmented closer to 1 AU, we see this kind of signal in the magnetic field, in angles of the magnetic field, and energetic particle flux enhancement associated with this clear rotation for characterizing the presence of magnetic islands. And here is how sometimes we can even see this with our eyes. It's heliospheric imagery observations from stereo A.
Olga,
Yes,
we lost your screen. It's now black. Could
really?
you move up or down?
Can you see now?
Okay. Now it's better. Yeah, just it's
Better.
now it's black again. Are you showing any movie or what? What is it?
Yes.
Maybe try to run it from here, not from the presenter's mode. Maybe we will be able to see it from here.
How can I do this?
Just put your mouse on. Is this a movie?
Yes.
So if you put it, it must show.
Does it? Can you see it now? Can you see it now?
Not really.
That's a pity. It's a very beautiful movie. Oh my God, that's really pity. That
Let's do a test. Let's stop your video, your own video. Maybe it's just internet is too narrow band on your side. Video from your web camera.
Okay. Just a moment.
Yeah, and now try again to launch your video. Maybe it will work.
Can you see anything?
Not really.
That's very bad. All right. What I will try to do, just give me 2 seconds. I can try to find it just as a real video. No, it's not that easy. It seems that we have to skip it, unfortunately.
Yeah, let's skip it for now. Let's come back to your presentation and turn on your web video again. So we will.
Can you see it? Can you see my screen?
Yeah, I see your screen. I don't see your video. So could you turn on your video from webcam, web camera?
Yeah. Ah.
Yeah.
Okay, I'm again with you. So unfortunately, you can see these nice observations from stereo A, and but actually sometimes, trust me, sometimes we can see these rows formed in the interplanetary medium, and now we come to the idea. Can you see my screen?
Yes.
Oh, good. We come to the idea that the magnetic islands are related somehow with the particle acceleration, and everything actually began with this work by Bill Matthews and co-authors, and they simulated processes of formation of magnetic islands. They were formed by turbulence, the result of turbulence, and they found that actually they see particle acceleration. And following this paper, there were a lot of papers, theoretical papers on simulations of processes of particle acceleration in magnetic islands and associated with current sheets. It's a kind of stochastic process. It was obvious that it's a kind of stochastic process because if you have reconnection here and there, then finally we can get this average particle acceleration. And here I just list some key papers on simulations and observations of particle energization associated with magnetic islands, dynamical magnetic islands. And the theory was built by Gary Zank and Carlos Leroux. And of course, it's talks about the first order Fermi energization and second order mechanism and appearance of anti-reconnection electric field, which can accelerate particles. There are some other effects, and if you read these papers published in the Astrophysical Journal, you will find a lot of interesting information. And what is important, that actually different mechanisms of particle acceleration, local particle acceleration in the solar wind, in the heliosphere, can be combined. And if we consider them even theoretically, the results will be very unexpected, I would say, and unusual, because what was shown in this particular paper, that if we consider only diffusive shock acceleration at the heliospheric termination shock, then the flux of amplification should be for these particles with these energies should be just 1. And if we see some extra particle acceleration, it comes from probably from the combination of 2 mechanisms of particle acceleration which occurs in dynamical magnetic islands and merging contracting magnetic islands and GSA. this is very important because every time when shock passes, we have this region behind the shock, downstream of the shock, filled with magnetic islands, with the current sheets and magnetic islands, which means that this is quite realistic situation everywhere in the solar wind. And actually we show this in different papers that yes, it occurs also in the solar wind, not only at the termination shock. And the second point I would like to highlight is that particles can be accelerated by different ways and sometimes different mechanisms. They interplay. And like here, you see this shock here, and particles which are definitely accelerated at the shock with diffusive shock acceleration mechanism. But if we come to higher energy particles, we see practically nothing here. But inside a fragmented ICME, where the mechanism related
Olga,
to yes,
4 minutes.
yes.
4 minutes to go.
Okay. And these energetic particle flux enhancements are technically related to processes occurring in fragmented ICME. So this is important. This new mechanism opens our eyes on processes of particle energization directly, which occurs directly in the solar wind. So let me summarize. We can accelerate particles locally in the solar wind up to several MeVs. If we trap them in magnetic cavities formed by different streams, by actually strong current sheets, and then if these magnetic cavities are filled with magnetic islands, dynamically magnetic islands, then you will get reacceleration of particles with quite high energies. And there is some movie formation of ripples of the heliospheric current sheets, which confine magnetic islands after the passage of ICME. Can you see the movie now?
Yeah.
Oh, that's good. There's something strange with that movie. And for example, this is an example of formation of very large magnetic cavities in the solar wind, again by propagation of different streams. And this is just, let me introduce our team, which works on these problems related to local particle acceleration associated with current sheets and magnetic islands. And this is a preliminary summary. As I told that if we observe energetic particles of keV, MeV energies at 1U and 5U in the solar wind, anywhere, actually they can come from different sources, and different mechanisms of particle acceleration can cooperate, can work together, and simultaneously we can get particles accelerated by different mechanisms. And just a very short part of this talk is about energetic particles at high latitudes, because actually usually people think that particles can get to high helium latitudes only because something happened at low helium latitudes, and then particles diffuse to high helium latitudes. As you can see, actually we can observe simultaneously coronal holes and active regions across the whole sun, both during solar minimum and solar maximum, which leads to complicated situations when particles can get to high latitudes by different ways. But what was the problem? That people think that shocks are not very active at high helium latitudes, so DSA doesn't work here properly, and that's why people came to the idea that there should be perpendicular diffusion, perpendicular to the magnetic field lines. And typically, diffusion in the direction perpendicular to the average field is considered to be orders of magnitude smaller, but sometimes this is the only way to accelerate particles to get them at high latitudes. But if you look at results, real observations, sometimes we see that partially nearly perpendicular transport really takes place, but partially it's not like this. And for observers, it's important to see that in the beginning of the event, just a moment. This is the particle first order anisotropy between the direction of energetic particles and the magnetic field. And if we expect them propagate along magnetic field, then we get this line. If we expect them propagating perpendicular, practically perpendicular, then we get this line. And practically what we have is half to half particles which are observed at high helial latitudes, they propagate in both ways. And what is important, in the beginning of the event, they propagate along magnetic field lines. And this is a big problem of observations of particles at high helial latitudes. You will look later at this slide, which is a summary of observations of energetic particles at high helial latitudes. Both the problems with time delays corresponding to perpendicular propagation. If we suggest that something occurs at low helial latitudes in the solvent and then propagate perpendicular to high helial latitudes. And the problems with shocks, which are not efficient at the higher latitudes anymore. So what we can suggest actually a mechanism which is very well known in the magnetosphere, which is interchange reconnection. When particles first reconnect here, and then they reconnect in the magnetic field. So this actually occurs at the Sun, and modeling shows this very easily, that we have a lot of situations when particles can be delivered to high latitudes by interchange reconnection at different active regions. And actually, how it looks like something like this. That the initial magnetic reconnection occurs, and the initial flare, for example, occurs at low helial latitudes, and then finally we get these particles to high helial latitudes by interchange reconnection. So in reality, everything is more complicated, and this is an example of how this interchange reconnection works. When practically simultaneously, we see several flares and several CNEs ejected from the Sun, and particles can get to high latitudes not from the initial CNE, but from the last CNE, which occurred here. And the final just note is that current sheets, which are formed at high helial latitudes, they play a role of tunnels for energetic particles. I don't have time enough for this. I'm sorry, we spent a lot of time solving the problem with the video. But anyway, what I can see here, I can show here that these tubes in magnetic field lines are formed inside the coronal holes during solar minimum, and it is confirmed by different ways. Both it's observed with magnetic field, it's observed with the speed, and it's observed by Ulysses. And if you read this paper, recent paper by us, you can find that Ulysses crossed this rotating tube inside the coronal hole several times in 1994, and we also saw it, observed it in 2007. And it's a magnetically dominated structure, which is very important because nobody expected this structure to survive to very far distances in the heliosphere. So these structures, conical current sheets, they play, as I told, a role of channels for energetic particles, and as well magnetic reconnection at the borders of these current sheets also takes place. So we see again both local enhancements and enhancements at the borders of the tube. No time to show this again. Sorry, I have to run forward. But it was observed both in 1994 and in 2007. And the explanation of particle acceleration occurring at the sun is that actually particles accelerated by magnetic reconnection again at the edges of this tube, which forms circle at the sun, and this idea we now developed this idea, selecting the events when we definitely saw this structure like conic-like current sheet, which can be traced, as I told, by magnetic field, by it's seen in the velocity, in the speed as well. It's a drop in velocity inside the high-speed solar wind. It's very interesting effect. And finally, if we trace the position of jets, polar jets, during some period, we will see a kind of rotation of the sun. And this simple movie shows how it occurs. Imagine that we trace the same position of at the foot point of this tube, which is circle now, and it rotates inside the coronal hole. This is the coronal hole. So we come to the result that these current sheets, conic-like current sheets, they rotate faster than the coronal hole, which also is confirmed by observations. So it brings us to the idea that we have a situation at high latitude similar to what we see at Jupiter. These are Juno observations of formation of this whirl inside the bigger one at the pole. And finally, these are my conclusions that actually, as I told, we can get energetic particles of keV energies in the solar wind and the heliosphere, which come from different sources, and particles can be accelerated by different mechanisms which coexist and interplay, and sometimes energetic particles are accelerated by one mechanism. They serve as seed particles for the other mechanism. And as well, when we talk about propagation and transport of energetic particles in the heliosphere, let's not forget about the existence of current sheets, which are channels for energetic particles. And let's think about magnetic reconnection occurring directly at the sun, not in the solar wind, not only the solar wind, and propagation of particles perpendicular to the magnetic field. So that's all. Thank you. Thank you for your attention.
Thank you, Olga. We have some time for questions or discussion. Please unmute your microphone if you want to ask a question and go ahead.
No questions.
For now, microphones are still muted. So let me ask a quick question. So
yes.
My understanding is that in the solar case, for solar flares, we have like low beta plasma, so we have a lot of magnetic energy compared with other forms. In the interplanetary space, beta is like larger, maybe about 1, so the proportion, the partition of magnetic energy is much smaller compared with other forms. So maybe the role of mechanisms is also different, in particular role of acceleration due to magnetic reconnection and magnetic energy. What do you think?
Actually, we have a paper with Valentina Zharkova. It's particle in cell simulations, and we showed that the Of course, there are some differences, but in the main thing, there is no difference because particles can be accelerated to rather high energies, and particles they behave practically the same as current sheets in coronal plasma, and there are a lot of similarities. Actually, it's a new project which we discussed with my colleagues of mine to compare magnetic reconnection and particle acceleration occurring due to magnetic reconnection in different plasmas, because there are striking similarities of the processes of this kind occurring in absolutely different plasmas. It's very interesting, and I can refer to our paper with Valentina. It's Astrophysical Journal 2012, and just 25th, perhaps, yes, 25th.
Okay, thank you. Other questions or comments?
Of
Hello,
course,
hello.
yes.
You hear me?
Yeah, just go ahead.
Okay.
Yeah.
Jiang,
Yeah,
it's you.
this is Chang Hu. Yeah,
Uh-huh.
at the UH.
Mm-hmm.
Yeah, I just have a question, maybe a request for clarification. I guess on the summary page, there's a bullet point about reconnection. I mean particle acceleration in high helio latitudes. So it was mentioned the interchange reconnection. So are you talking about that reconnection happening fairly close to the sun? The particles accelerated through the reconnection process, then kind of propagated out? Or are you talking
Yes.
about, so that's kind of different from relative
No, it's
local.
exactly as you told. Look, if I have this interchange reconnection, just let me show this here, for example. If you have magnetic reconnection here, the particles, then magnetic field lines, they become open here and come here to higher latitudes, and particles can be reconnected again, accelerated again due to reconnection at higher latitudes. So practically during every phase of the solar cycle, this reconnection, interchange reconnection, can occur in different configurations, not only because we have active regions. For example, during the solar minimum, we don't have many active regions, but still at high helio latitudes, we have coronal holes. And inside coronal holes, we have magnetic reconnection too. It's not a unipolar region as many people think. If you look deeper, you will see, otherwise we would never see these polar jets inside coronal holes, as we exactly showed here. Excuse me, let me come back to our final results about this. Yes, these are, these are coronal polar jets, which are observed inside coronal holes, which means that we have differently oriented magnetic fields inside coronal hole. And to us, some of them occur at this foot point of this conic-like current shape. It becomes quite obvious. So this is also a kind of interchange reconnection, because if something happens here, the second event can happen here because of this running reconnection. Was it what you wanted to hear? Did I answer your question?
Yes, more or less.
Okay, thank you, Olga. If we have One more reasonably quick question. We have a little bit of time.
I think that people always can contact me via Skype or
Yes,
by
there
email.
is an option to send a question for follow-up session, but now I don't see any further question, and in fact our time is over. So let me thank Olga again and thank all participants for joining us. So thank you once. Stay
Thank you.
tuned. We are to meet in 4 weeks again. Thank you. Bye.
Thank you. Bye.
Thanks. Thanks, Olga.
Thanks. Bye.
Bye.